Here I've got section A. This is of the Unit 5 worksheet 2011-2012. So question 1. Two rectangular blocks X and Y of the same material, that's important, have different dimensions but the same overall resistance. Which of the following equations is correct? Now, obviously when looking at these, I can see that I've got the resistivity, length, cross-sectional area. I must be dealing with this formula over here. Now we're told that the resistance is the same and the material is the same, so the resistivity of both X and Y must be the same. That must be the same, that's the same. So if I put these together then, because R of X is equal to R of Y, I can say rho L of X over area of X must equal rho L of Y over area of Y. And so these two will cancel, these are the same, so I can see that B would be my correct answer there, that the length over the area is equal to the length over the area. Okay, going on to question 2. It says two 6 ohm resistors are connected in series with a 6 volt cell. A student incorrectly connects an ammeter and a voltmeter as shown below. So we've got the voltmeter in series. Now a voltmeter is very high resistance. It's actually got infinite resistance, an ideal voltmeter. And your ammeter has got very low resistance. So in actual fact, what's going to happen is that you've effectively just got a voltmeter. There's going to be no current flowing because this resistance is so high. Your current in your circuit, actually let me do it this way, your I is effectively going to be 0 amps, because remember I from this formula over here is equal to V over R, and because R is so big, because that's infinite, basically your I is going to be 0. So we're definitely going to get a 0 reading on the ammeter. There's going to be no flow of current through here, because so that's going to be 0. So we're actually looking at either A or B. But which one of these? Now this effectively becomes a voltmeter over your 6 volt resistor. So in actual fact it's going to be this over here, because this voltmeter just goes over the 6 volt cell. There's no current, so it doesn't lose any potential difference across there, so it will be 6 volts. So to actually be B is the correct answer here. We have the diagram shows a potential divider circuit. In order to increase the reading on the voltmeter, now for this one over here we're going to have D, it's going to be 3D. The light intensity of R should be decreased. As you increase the light intensity on R, the resistance actually gets bigger. When you decrease it, the resistance goes down. And because V is equal to I times R, as your resistance gets bigger or smaller, your voltage gets bigger or smaller. So the answer to that is going to be D. Looking at question 4, it says a tungsten filament of a lamp has a cross-sectional area of A and a length A tungsten filament of a lamp has a cross-sectional area of A and a length L and a potential difference V across the filament. The current in the filament is I. The resistivity of the tungsten equals. Now we basically got this over here, this formula, and this other formula over here. So R is equal to rho L over A, and it's also equal to V over I. So rho is therefore going to equal AV, and this over here, this A is the area, over Li. So let's have a look which one. This one over here would be, it looks like this one, VAIL. So it's going to be that one over there. Going on to question 5. Which of the following is the correct unit of the electromotive force? Well, the electromotive force, the EMF, is a potential difference. Remember, your formula for that is V is equal to W over Q. So it would be a joule per coulomb. This is energy and charge. Alright, so it would be this one over here, it would be 5D. Question 6. Which of the following correctly gives the resistance of an ideal ammeter and the resistance of an ideal voltmeter? Well, we had a look at that before. And an ammeter is always in series, and therefore you want zero resistance, so either here or there. A voltmeter is always in parallel, so you don't want any current to really go through the voltmeter, so it needs to be infinite. So it's this over here, so it's going to be C. That would be correct. So whenever you have a ammeter, it's always in series in the circuit, and a voltmeter is always in parallel. So what actually happens is that if I just connect this up to some sort of resistor there like that, all the current actually goes through the resistor or through the ammeter, but you don't want any loss of energy through there, so it must have zero resistance. Because the voltmeter is in parallel, you don't want any current going through there like that, and therefore it needs to be infinite. Question 7. A cell of EMF E and internal resistance R delivers current to a small electric motor. So we have 450 coulombs of charge flows through a motor, and 9,000 joules of energy are converted in the motor. 1,800 joules are dissipated in the cell. The EMF of the cell. Now remember, the EMF is the total energy per coulomb that a cell can deliver, and that includes the internal resistance. So it's going to be basically both the V, the potential difference across the motor, and also your potential difference across your internal resistance. Now V is equal to W over Q. So for the motor, it's going to be 9,000 joules per 450, and we divide that out, that's about, turns out to be 20. And for your small resistor R, it's W over Q, and that's going to be 1,800, and it's also 450 coulombs, because this is a series circuit. So any charge that goes through the motor will also have to go through the resistor. So it would also go through there, and that's going to be 4 volts. So 20 plus 4 is 24, so your answer is D. Question 8. It says a cylindrical conductor, length L and diameter D and resistivity ρ, has a resistance R. A different cylindrical conductor of resistivity 2ρ, length 2L and diameter 2D has a resistance of what? Okay, so we have this formula that R is equal to rho L over the area. But remember, this area is equal to pi R squared. So I could write this as rho L over pi R squared. That may be better. So in the first one, that's our resistance. Now what about the second one? Well, we've got 2 rho and we've got 2L, but we're going to have pi, but the radius, because we're talking about the cross-sectional, the diameter is doubled, so the radius will also double, so it's actually going to be 2r. So it's going to be 2r squared. So it's going to be 4 rho L over pi, but this is going to be 2 squared. It's going to be 4r squared there. So that 4 and that 4 is going to cancel, and you're left with rho L over the area, which is the same as r. So it's going to be B. It's going to have the same resistance. Looking at question 9, we have in a circuit below, the cells have the same EMF and 0 internal resistance. The resistors all have the same resistance. Now, which of the following gives the ratio of the power dissipated in X, the power dissipated in Y? I would probably use this formula over here, that power is equal to V squared over R. That's going to be the one that we can use. We know that the V is the same, the EMF is the same. If for these over here, let's just say this is 2 ohm and 2 ohm. Sorry, there. And this would therefore be 2 ohm, 2 ohm. So here we're going to have a resistance of 4 ohm. And here I'm going to have what? I'm going to have 1 over 2 plus 1 over 2 is equal to 1 over RT. So a half plus a half is 1 over RT. So my total resistance for this is actually 1 ohm. I could replace these two here by a resistor of 1 ohm. So when I look at the power in this one over here for X, it's going to be V over 1 squared, and for the power in Y, it's going to be V squared, not over 1 squared, because here we've got, it's just R, so it's just divided by 1, and the power in Y is going to be the same V squared but over 4. So we're going to have, therefore, the power in X is going to be 4 times greater than the power in Y. So D would be your correct answer there. Looking at 10, it says a point charge of magnitude 2 microcoulombs. I hope you understand this micro is actually 10 to the minus 6. You need to know these. Is moved between points X and Y. Point X is a potential difference of 6 volts and point Y is a potential difference of 9 volts. The gain in potential energy of the charge is. Now we know that V is equal to W over Q. Therefore W, which is work, which is energy, is equal to V times Q. So it's a multiple of this. So it's 2 and it goes from 6 to 9. So there's an increase in 3. So the change in voltage here is 3. Change in potential difference. So it's going to be 3 times 2, which is going to equal 6 microjoule.